In February 1987, the Defense Science Board published a report titled Defense Semiconductor Dependency. It said that the superiority of America's defense depended on superior electronics, which in turn depended on a healthy American semiconductor manufacturing industry. But throughout the 1980s, American companies lost share and leadership in semiconductor manufacturing. The Americans had 67% market share in 1975, but 10 years later, in 1986, that had fallen to just 50%. To fix this, the report proposed a Semiconductor Manufacturing Technology Institute. It would be partially funded by the Department of Defense and be staffed with people borrowed from the industry. This institute would work directly with American manufacturers to develop and transfer new equipment so that America retains the lead in high-volume semiconductor production. Thus, in May 1987, we got that institute, Semiconductor Manufacturing Technology, or Sematech. In this video, we look at one of the most famous and impactful consortiums in semiconductor history. The report from 1987 attributed America's perceived semiconductor decline to a series of factors. It pointed to the rise of the Japanese semiconductor makers like Toshiba, Hitachi, or NEC. They highlighted the fact that those companies were highly vertically integrated, consuming up to 20% of their own production. It also pointed out that Japanese companies had access to very cheap sources of capital. Not only government subsidies, but also profits funneled into their semiconductor divisions from the rest of the conglomerate. Samsung benefited the same way. Concerns about Japan's semiconductor rise were fanned by American anxieties and Japanese nationalists. One particularly infamous quote by Shintaro Ishihara, a novelist turned politician who I shall euphemistically call an ultra-nationalist, went, "If Japan told Washington it would no longer sell computer chips to the United States, the Pentagon would be totally helpless. Furthermore, the global military balance could be completely upset if Japan decided to sell its computer chips to the Soviet Union instead of the United States." This quote came from Ishihara's 1989 book, The Japan That Can Say No. Ishihara was a novelist, not an industry man, and his words demonstrated a profound misunderstanding of the semiconductor industry, its history, and its capacities. But it nevertheless galvanized the American public towards action. Setting aside Japan, the report also double underlined issues in the manufacturing side of the American industry. Companies had strong advantages in semiconductor design, and in marketing, they also had the largest consumer markets. Japan, however, held a very strong edge in manufacturing. The key to leadership in semiconductor manufacturing is high volume. The more wafers you have flowing through your fabs, the faster you can work through issues and hit higher yields. The U.S. semiconductor industry might have first grew up on massive purchases by military organizations like NASA, but by the 1970s, the volumes in the military market had long paled compared to what is available in the commercial market. And that side was where the Japanese strengths were, thanks to companies like Sony, Panasonic, and Sharp. Charles Spork of National Semiconductor liked to show a chart projecting America's worldwide semiconductor market share out to 1999 based on 1984 trends. By 1999, the United States would have 20% market share and the Japanese 60%. Now, calls for the American semiconductor industry to band together have been around for a while. In the late 1970s, Japan used consortiums to significantly upgrade their semiconductor industry, the most famous of which was, of course, the Very Large-Scale Integration Project. It lasted from 1976 to 1979, after which Japan dramatically raised their worldwide share in memory. Drawing the line between cooperative projects like VLSI and Japan's success was easy. Senator J. Bennett Johnston of Louisiana said, "What we have seen in the Japanese model is that a consensual society can do some things better than a strictly competitive society. The great secret is that they, the Japanese manufacturers, undertake long-term strategies." The United States is familiar with R&D consortiums, where competing players work together on research and all share what they learn. They had once been common in the banking and railroad industries before the Sherman Antitrust Act of 1890 made them illegal. The issue with Japan's VLSI project example is that a number of American semiconductor companies had been banding together, sometimes even led by government, without very transformative results. In 1980, the Department of Defense established the Very High-Speed Integrated Circuit Project, which was meant to leverage private industry innovations for military R&D. In 1982, the Semiconductor Industry Association, or SIA, had established the Semiconductor Research Corporation, a consortium sponsoring long-term research at various locations. And then in 1983, we had the Microelectronics and Computer Technology Corporation, an R&D consortium made up of a diverse set of American technology companies. These efforts failed to reverse the declining competitiveness of the American semiconductor industry. So what is the United States going to do differently this time? From the very start, Sematech's overarching goal was to improve the competitiveness of American semiconductor manufacturing. Nobody disagreed with that, but there was plenty of disagreement over how to actually do it. Gordon Moore of Moore's Law thought Sematech should be a consortium that directly produced memory chips in order to, quote, take back, end quote, America's lost ground. While the press hyped up such an idea, it was not only financially unviable, but also meant that Sematech would compete against some of its own members. Academics studying Japanese semiconductors came to the conclusion that Japan's production advantage stemmed not from superior tools or technology, but rather how they implemented those tools and technology. Previously, American semiconductor companies always invested for the next game breaker. Sematech's thesis revised that. Semiconductor manufacturing excellence would have to be built on top of evolutionary improvements rather than revolutionary breakthroughs. This was reflected in the technical goals that Sematech set out for themselves to achieve over the next few years. First, hitting the 800 nanometer node by 1989 on 5-inch wafers. Then after that, hit the 500 nanometer node on 6-inch wafers by 1991. And then finally, their Phase 3 technical goal, 350 nanometers on 8-inch wafers by 1993. If Sematech hits all three phases on schedule, then they can make the credible argument that the US manufacturing industry had reached parity with the Japanese. There were 8 other objectives as well. Most of these involved developing relationship with suppliers, testing equipment, and facilitating continued technology advancement. Sematech's founding member companies made up 85% of the American semiconductor industry, and at this time they were specifically American companies. NEC had a facility in the United States that had their membership application rejected. Congress awarded Sematech $100 million a year from 1988 to until 1993. The state of Texas, where Sematech would be based, put up another $50 million, and the member companies themselves contributed another $100 million to reach the final budgeted number of $250 million. Sematech drew about 200 employees from its member companies who rotated there for 2-year stints. The organization also had direct hires for running administration and support tasks. In terms of governance, there was a board of directors that sets general direction and policy. There is also an executive technical advisory board that recommends and approves R&D projects. As a whole, Sematech was quite a flat organization. You have project managers, and directors reporting to a single CEO. Finding the right person to lead Sematech was critical. This CEO would have to handle the Defense Department and Washington politicians. They would have to command the respect of the sprawling, ultra-competitive semiconductor industry, and they also need to have significant technical chops of their own. Such a person was a unicorn. Most people of that caliber can either get much higher salaries at the companies themselves, or were not willing to uproot their families to go to Texas. Robert Noyce and Jerry Sanders led the search. Noyce was one of the statesmen of the American semiconductor industry. A member of the Traders' 8 who founded Fairchild, he co-invented the integrated circuit and then co-founded Intel. At the start, Noyce did not want the job. He was 60 years old, already had a job as vice chairman of Intel, and had personal commitments. So at the start, he took himself off the list. They had first offered the position to 2 people, Gil Amelio, who was then president of the semiconductor division of Rockwell Communications. Amelio was close to accepting before ultimately taking a promotion at Rockwell. He later joined National Semiconductor and turned them around. Then he jumped ship to Apple Computer and went down in history as the CEO before Steve Jobs took over. The second guy was Bob Palmer, head of Digital Equipment Corporation's Semiconductor Operations Division. Palmer became CEO of the declining DEC, overseeing thousands of layoffs and the eventual sale of a once proud computer giant. The search for a CEO dragged on. A managing committee of 3 guys was running the organization on a day-to-day basis, and confidence started to flag. In perhaps a sign of their displeasure, the Senate passed a version of the appropriations bill with just $44.8 million for Sematech rather than the anticipated $100 million. Noyce must have felt that Sematech would sink without immediate leadership. Sometime in June 1988, he and his wife went to Aspen for a vacation, where he changed his mind and decided to be CEO, saying, "Damn it, it will be fun. It will be work, but it will be fun." Noyce's signing delighted everyone and locked down congressional funding for Sematech. Charlie Spork, CEO of National Semiconductor, said that Noyce's signing basically saved the organization. If Noyce had not accepted the job, Sematech would have faltered from falling off of interest. One of Sematech's first tasks was to build their operating fab on the University of Texas campus. This was done by Sematech's first COO, 30-year IBM veteran Paul Castrucci. The son of Italian immigrants, he pushed hard to build a world-leading operating facility, a shining example of America's capabilities. The fab was completed in just 9 months on November 1988 at the cost of $75 million, an impressive achievement. The fab's opening ceremony had much fanfare and even a flyover by some jets. Shortly thereafter, Sematech started its first technology transfer session, a workshop with member companies on how to build a fab as quickly and cheaply as Sematech did. The workshop went deep into specifics, revealing best practices for improving the speed of the build. It was the first sign of what would eventually come to be Sematech's way to upscale the American semiconductor sector. As I mentioned, everyone knew what the main goals were, to help boost American manufacturing, but people had different visions on how to achieve it. Castrucci and Noyce were 2 such people, and a few months after Noyce joined, Castrucci resigned, bowing out so that Noyce can install his own consensus-driven management style. Turner Hasty took over as COO, a Texas Instruments veteran who can handle administrative matters, while Noyce built consensus and fleshed out the mission. That mission soon came to settle on the American semiconductor equipment industry. The collapse of the American DRAM industry helped bring Sematech into being, but Sematech gradually shifted its work focus from producing dynamic RAM chips, or any other product for that matter, to manufacturing equipment. This was the number one concern. In 1979, the top 9 semiconductor equipment manufacturers by revenue were all American, with Fairchild, Perkin-Elmer, and Applied Materials in the top 3. But the Japanese made steady ground throughout the 1980s. By 1989, 4 of the top 5 suppliers were Japanese, including the top, Tokyo Electron. Applied Materials was the lone American holdout. One of the reasons for this decline was the rapid acquisition of American producers by foreign producers. For instance, the 1989 acquisition of Monsanto Electronic Materials, America's last silicon wafer maker, by the West German company Wells AG for $250 million. Moreover, Japanese semiconductor manufacturers only really bought from Japanese suppliers, usually one in their own corporate family. So the more share Japan won of the semiconductor industry, the smaller the pie got for the American equipment makers. The biggest risk, the one that most alarmed Intel, National Semiconductor, and the other American companies, was that there was no guarantee that Japanese suppliers will give them the best product. Craig Barrett at Intel told a story of a meeting in Japan. "I was at a semi-meeting in Japan where the representative from Nikon stood up and said, When appropriate, we may even tell our foreign customers about our new equipment. Nikon happens to be our supplier, and it's nice to know that, when appropriate, they might even tell us about the next generation. At this point, it started to become more clear to the people at Sematech that a possible way to shore up American manufacturing was to help the American toolmakers. The idea of targeting manufacturing was an elegant solution to get the member companies to work together without having the consortium compete with any of its member companies. There was a lot that they could learn from one another. Prior to Sematech, every manufacturer in the semiconductor industry worked off of proprietary internal guidelines. Anyone opening up their standards to others was trying to get paid for it. Sematech offered a neutral third party to circulate best practices. For instance, Dean Toombs brought with him Intel's rigorous program of qualifying equipment vendors before putting them into the fab. For the toolmakers, Sematech helped them solve a long-standing Babel problem. Previously, a semiconductor company would approach a toolmaker with a specific need. The problem was that that need was so specialized that the toolmaker could not build what was essentially a custom tool and make their money back. So the first question the toolmakers always ask was something like, is IBM in on this? What Sematech did to deal with this was to institute broadly accepted standards that are still flexible enough for individual users to customize in the fab to their liking. That way, the toolmakers can spread their costs over a swath of customers. Noyce's vision for how Sematech was to work was described as define, develop, and demonstrate and transfer. First, they wanted to define a set of standards in line with their overarching technical goals. Then Sematech wanted to develop the materials, tools, and technologies to help hit those goals. In universities around the United States, Sematech set up 10 centers of excellence to research and locate interesting technologies. They also struck deals with national science labs to develop new tools. Once those tools are developed, Sematech would then demonstrate those tools to companies in the industry. If the companies choose to accept it, then those are transferred over. Starting in 1989, when Sematech signed its first contract, the consortium struck deals with over 100 companies. Some of these are in the form of joint development R&D projects, co-working with an American supplier to develop some future generation technology, like for instance working with Drytech in Massachusetts on low-temperature plasma etching, or Silicon Valley Group on advanced lithography. Then there are the equipment improvement programs, where Sematech works with the supplier to upgrade existing equipment to meet manufacturing requirements. For instance, working with Applied Materials to improve the Precision 5000 chemical vapor deposition system. Early on, Sematech struggled to get industry companies to accept these demo projects. Fabs were not always excited to test experimental equipment on real production lines. That had been one of the benefits of the Japanese way of doing things. A member of Nikon commented, "A customer gets early access and headaches. Before we do that, we've got to be convinced our relationship will survive some of the bumps. It can affect your long-term business." But Sematech pushed on, and some of the grants started to succeed. One example project was in 1990 between Sematech and Lam Research for a chemical vapor deposition process. Sematech arranged for Lam's tool to be used within their own fab. The process was long and difficult, but ultimately successful, yielding $150 to $200 million in sales for Lam. Another one was Genus Inc., which had worked with Sematech on a chemical vapor deposition system for selective tungsten films. Genus management later told the New York Times in April 1991 the product failure rates declined and sales grew stronger as a result. On June 3, 1990, Robert Noyce unexpectedly passed away from a heart attack while at home in Austin. He was only 62. Noyce's passing was an unfortunate tragedy. Nevertheless, he had felt that his time as CEO had helped Sematech get off the ground, attracting the necessary financial, human, and political resources to carry out its mission. So shortly before his death, Noyce had already told Sematech that he would be stepping away as CEO to focus on lobbying and being a public face. He had drawn up a list of 8 potential replacements. A search committee replaced him in October 1990 with the relative unknown William Spencer. He had worked at Xerox, heading up their well-regarded research laboratory as their chief technical officer. Spencer joined the organization at a rough time. Members of the Ronald Reagan administration had objected to doing the first Sematech project, pointing to the government's previous attempts to regain market share, as well as President Jimmy Carter's other attempt to develop petroleum alternatives with the Synthetic Fuels Corporation. Synthetic Fuels received a budget of $20 billion to develop alternatives to imported fossil fuels. But after 6 years, the company only spent $960 million on 4 synthetic fuel projects with no outcome. Reagan ended the project when he entered office, seeing it as a failure. So Reagan had been skeptical about Sematech, but they still let it through. After he left office and George H.W. Bush came to power, the elder Bush was even more skeptical of the project. Thanks to Sematech's efforts, American semiconductor equipment makers gained share, registering an increase from 38% market share in 1990 to nearly 40% share a year later. But this success was tainted by a significant business failure in lithography, particularly that of GCA. GCA had once been America's leading lithography maker, but their machines, which were not patented, did not perform well. Nikon and later Canon copied and improved the tool, eventually leapfrogging GCA to become number 1 and 2 in the industry with a cumulative 80% market share. The struggling GCA was eventually sold to the conglomerate General Signal, together with Silicon Valley Group, which had earlier been saved through the efforts of IBM. They were the last American lithography companies in the market. Lithography is extremely important to the semiconductor manufacturing process, a key driver of their increasing sophistication. Fabs, even American ones, were wary of using what they saw as an inferior tool. Sematech set up an expensive multi-million-dollar project to improve GCA's machines. To lower the risk of adoption, Sematech offered to buy machines themselves and consign them to fabs. Any learnings would be circulated across all the fabs. As I covered in a previous video, the company's products did indeed improve. The XLS received great praise by American chipmakers like DEC, who chose them over Japanese tools. However, by 1992, GCA only held 2% of the market. Without the necessary scale, they were losing $4 million a quarter in the early 1990s. With the semiconductor industry going through another downturn and GCA missing a critical window due to an 18-month delay in 1990 in producing eye-line lithography equipment, they could not sustain any further. After spending millions of dollars, somewhere in the range of $30 to $80 million, Sematech ultimately did not find it politically viable to intervene any further. And even with the government promising some form of vague financial support, corporates like AT&T opted not to bail them out. So GCA eventually closed down their lithography business in late 1992 and early 1993. The final factory in Andover, Massachusetts, shuttered in May 1993 with 120 jobs lost. On top of that, just a month earlier, in April 1993, the only other American lithography maker, SVG, announced a partnership with the Japanese Canon. That news was not well received in Congress. SVG later sold themselves to ASML after a botched 193nm transition. As its 5-year mandate came to an end, Sematech wanted to continue their mission, and a number of its member companies wanted to as well. Now Congress just has to agree and renew its funding, which would be difficult in an era of reduced Defense Department spending. In response, CEO William Spencer told Congress that he planned to cut the total budget by 10% and reposition Sematech for a new role. And in December 1992, Sematech received 2 major boosts of credibility. First, Sematech announced that they had achieved their Phase 3 technological milestone. If you recall, they wanted to hit the 350nm node on 8-inch wafers by 1993, and they made it. Second, the Americans were taking share again. Japan's market share peak was in 1988, when the Japanese had 51% and the US 37%. The trend then started to reverse in 1991. Then, end of 1992, VLSI Research, a semiconductor research firm, issued a market report, finding that U.S. firms had pulled ahead of the Japanese for the first time in 8 years. The Americans, with Intel and Motorola as leaders, had 44% of the market by revenue. The Japanese had 43%. VLSI Research attributed this turnaround in part to Sematech's efforts, pointing out that improvements in American semiconductor equipment vastly improved reliability and cut the Japanese advantage in yields from 50% in 1985 to just 9% in 1991. A 1991 survey showed that U.S. semiconductor firms expected to purchase 40% of their equipment from American equipment makers. In reality, they instead purchased 70%, a surprise to the upside. But not everyone saw value in Sematech. First, Congress was unhappy with the losses of American lithography, and then there were several major defections from the consortium: LSI Logic, Micron, and Harris. In 1993, one of the founding members, LSI Logic, announced their departure, their reasons being disagreements with the agenda, which they saw as being driven by the big companies as well as financial difficulties. Micron left after that, one of the last big American memory makers. LSI and Micron had not been a particularly big deal since they had been small at the time, less than $500 million in revenue, but that last departure, Harris Semiconductor, was felt as a major loss because their biggest customer is the Department of Defense, whose budget was partially funding Sematech. Harris focused on lagging-edge chips for the military and so wanted projects to improve reliability and ruggedness in their chips. Sematech could not accommodate that, so Harris pulled out so that they can reallocate their dues for their own internal R&D programs. But President Clinton liked the idea of Sematech being an example for future consortiums in the industry. He allowed for the funding, but cautioned in a report at the time that the government would not be able to sustain the level of funding down the line. In line with his comments, Spencer jettisoned the idea of Sematech building and running fabs and showing other people in the industry how to do their jobs. Instead, they settled on a roadmap process, a way for all the members of the semiconductor industry to systematically join together to work out the details of next-generation semiconductors. The roadmap will coordinate the required timing, identify potential showstoppers, and intensify R&D to solve those showstoppers. Other organizations had set up their own roadmaps. For instance, in April 1991, there was the NACS and their Microtech 2000 roadmap. Microtech 2000 had brought together the splintered industry for the first time, a mighty achievement. Its goal was to identify and map out the path to a 1 GB SRAM with 120nm feature sizes by 2000. But members criticized the actual roadmap for being impractical. For instance, it required an ambitious one-generation leapfrog, and it ignored the factor of cost and feasibility. The members could not adopt it, and later that year, the NACS dissolved and handed the Microtech roadmap over to the SIA. Later, in November 1992, before Sematech had to go back to Washington for more funding, they joined together with SIA to produce a 10-year plan, the National Technology Roadmap for Semiconductors, or NTRS. This one stuck, and the industry even hit the next forthcoming node, 250 nanometers, ahead of schedule. 2 years later, Sematech and 300 experts went to Boulder, Colorado to update the roadmap. With the warmth of the 250nm node beaming on their faces, Sematech and the rest of the industry sought to accelerate the timing of new node introductions for Sematech members from the historical 3 years down to just 2. Publishing this roadmap was a big but calculated risk. Having it be public meant that everyone, including the Japanese, could read it too. Openness works both ways. Spencer realized that in order to really drive change in the industry and hit the roadmap, Sematech needed to get deeply involved in how member organizations take up new technologies. Let us go back to the process that Sematech discussed for inserting technology into members' fabs: define, develop, and demonstrate, and transfer. It is the transfer part that Sematech needed to take a closer look at. For firms to get the ROI on their investments, which came in the form of the dues in which they pay in, and the people they lend, they had to get real tech really working on their real fab floors. So Spencer focused on driving that and not just calling it a day with the report. These efforts succeeded. American equipment firms migrated to the bleeding edge of all areas of semiconductor manufacturing, with the exception of EUV lithography, of course. And until around 2003-2004, the industry kept up its manic 2-year cadence of introducing brand new process nodes. Per Moore's law, a node shrink brings significant economic advantages. Smaller feature sizes cut per transistor costs and gives the cutting-edge node leader a cost advantage over its rivals. So the Americans left the Japanese in the dust. In October 1994, Bill Spencer reported that American microchip makers had nearly 48% market share of the semiconductor industry. The Japanese were rapidly fading with just 36%. Then, shortly after Congress approved funding for the fiscal year 1995, Sematech announced that it would forego government funding starting in the 1996 fiscal year. It was a surprising move, but it was a calculated one. Congress was philosophically against the idea of indefinitely continuing Sematech funding. And the people of Sematech pledged from the very start that government involvement in the consortium would not be so anyway. Japan's original VLSI project lasted for 4 years, and that was that. Why should they keep giving more budget in that case? Spencer wanted Sematech to stick to their word and show the public that they were not an entitlement project funneling government money to industry. It would set an example. There would be one more $90 million grant from ARPA for current technology projects. After that, Sematech would rely on just its member dues as well as federal research grants, which it would need to compete for just like any other organization. After Sematech stopped taking government funding, the organization opened itself up to international semiconductor makers the next year, ushering in a new era for its role in the industry. It is remarkable to think what Sematech has been able to do. A single organization brought together the US's biggest semiconductor makers into a neutral setting to hash out big problems, kind of like the United Nations. As a result, the industry settled on a set of widely accepted standards to help facilitate lasting relationships between the semiconductor manufacturers and their equipment suppliers. But did Sematech really save the American semiconductor industry? At the heart of it, the industry saved itself, but I largely agree that Sematech made significant contributions to American manufacturing. That being said, let's dive into it. To me, the crucial data point is the reversal in market share that American semiconductor companies experienced from the mid-1980s to the early 1990s. Sematech did help with this by boosting the reliability of American equipment makers and helping to ship newer and newer nodes. But there were other things happening during this period of time. First, the 1986 US-Japan Semiconductor Trade Agreement not only restrained Japanese sales of memory chips into the United States, it also required that the Japanese raise their proportion of foreign-made components in its domestic market to 20%. By the end of 1992, this had been achieved, with U.S. makers benefiting the most from these share gains. Second, this time period also covers the rise of the Korean memory makers. We should not understate the impact of Samsung, Hyundai, and others entering the market, catching up to the leading edge, and surviving through the market implosion. Not to mention the Taiwanese semiconductor makers like TSMC and UMC, which started out in memory making but ultimately left that market too, as it shrank from a peak of $40 billion in 1995 to $13 billion in 1998. Sematech's effects in the manufacturing space also need to have other things to be taken into context. First, the aforementioned loss in litho with GCA a significant blemish. Sematech had invested a considerable portion of their R&D budget into lithography, but while they were able to boost the company's technical chops, they could not reverse its business struggles. When GCA shut down, that went all for naught. Second, the U.S. memory chip industry was largely lost. Most of the former players had been forced to drop out of the industry. Only Texas Instruments and Micron were left, and Micron left Sematech, as you recall. The shining example of American semiconductor manufacturing was Intel, but they only ascended to their current status after they left memory. Remember Spork's chart, the one projecting U.S. market share out to 20% in 1999? 22 years later, in 2021, the SIA pinned the U.S. market share in wafer fabrication out to just 12%. So Sematech slowed the decline, but the direction has largely continued downwards. The semiconductor industry has greatly changed since the 1980s. It is more consolidated, more capital intensive, and more international than ever before. Sematech was the right solution, hitting the right problem at the right time. Whatever ails the American semiconductor industry today, if it at all does, since American design still unquestionably leads the world, the solution will need to be something new. Alright everyone, that's it for tonight. Thanks for watching, or listening I guess. Subscribe to the channel, like this video and all, and I'll see you guys next time.